Well, a warm welcome to another in this series of video presentations in the role of bisphosphonates in the treatment of Pagets. So my name's Stuart Ralston. I'm chair of the Pagets Association, and we're presenting these videos in celebration of Pagets Awareness Day on the 11th of January 2021, which marks the 207th anniversary of the birth of Sir James Paget. So today it's my pleasure to welcome all the way from Australia, Professor Mike Rogers, who's kindly agreed to talk to me about the work he's conducted on the mechanism of action of bisphosphonates. So, Mike, perhaps you could say a few words about yourself, your career, and how you got involved in this field. Over to you.
Sure. Thanks, Stuart. Great to see you, and thanks for the chance to join you in these presentations for Paget's Awareness Day. So, my research career began in the mid-1980s. I did a PhD in the University of Sheffield after studying the biochemistry there. And that's really where I met Graham Russell in the Department of Human Metabolism and Clinical Biochemistry in the Royal Hallamshire Hospital. So Graham, of course, was one of the people who identified the properties of bisphosphonates, their pharmacological activities, along with Herbie Fleisch and Dave Francis. So Graham was really had this great idea of using slime molds to actually study how bisphosphonates might work. At that time, we didn't know how bisphosphonates blocked bone resorption, bone loss at the molecular level. So my PhD studies with Graham showed that bisphosphonates actually work in the same way on slime molds as they do on osteoclasts. So that really set the scene for the next few years. I worked as a postdoc in Sheffield. And then in 1997, I moved to the University of Aberdeen, where I worked with you, Stuart, for about 10 years. We worked together. And I became interested in studying the effects of bisphosphonates, not just in bone, but also what effects they might have outside bone, such as their anti-tumor activity. And then in 2012, I moved from Aberdeen to Sydney, to the Garvan Institute, where I'm now a lab head there. I have to say I don't miss the climate in Aberdeen at all, but I do miss the fantastic scenery in the Highlands.
Okay, thank you, Mike. As you've alluded to, you did some work on the mechanism of action of bisphosphonates, and in another interview in this series, I had interviewed Graham, who mentioned to me at the very start they knew bisphosphonates bound hydroxyapatite, they bound to bone, and they thought it prevented the bone being dissolved. Now, as you've hinted, we know that's not the case. So maybe you could tell us back to the work you did in the 1990s with, I think you were working with one of the, what we call first generation drugs, Claudrin 8, and you figured out how those were working. So maybe you could tell us a bit about that story.
Yeah, so that's an interesting story. So the breakthrough in understanding how Claudrin 8 works actually came about through studies on these slime molds called diptyostelium. So the idea behind that was actually came from a group in France who were trying to measure the acidity inside these slime mold cells. So part of the life cycle of the slime molds is that they grow as unicellular amoebae. And what this group found was that very simple bisphosphonates could actually be converted in these slime mold amoebae and metabolized into a more toxic molecule that actually blocked the growth of those slime mold cells. So this led us to the idea that maybe Claudrin 8 could also be converted in the same sort of way to a toxic molecule inside the slime mold cells. And we proved that that was actually the case. And Claudrin 8 is converted to a form of a natural molecule called ATP, a really important energy containing molecule. But that toxic metabolite stops the cells from growing. So the final piece of evidence was that we showed that Claudrin 8 could also be converted to this toxic molecule inside osteoclasts. And that involved a collaboration with a good friend of mine, Jukka Monkonen, and his colleagues in the University of Kuopio in Finland. And we showed that osteoclasts produce that toxic molecule and it stops the osteoclasts from working. And that's really how we think Claudrin 8, probably also atidronate, actually blocks bone resorption by being toxic to the osteoclasts.
Thank you. And as you know, clodronate is one of the earlier bisphosphonates. You mentioned etidronate, which we've talked about as well. And we're now pretty much using nitrogen-containing bisphosphonates, or amino bisphosphonates that are sometimes known. And you've done work in that as well. And my understanding is those work in a different way still. So maybe you could tell us a bit about that story too, and what's going on there.
So that was another interesting story. Again, really using slime molds as a peculiar model of osteoclasts actually led us to understand how those drugs work as well. So what we found with the slime molds was that those nitrogen-containing bisphosphonates, the amino bisphosphonates, didn't seem to be metabolized in the same way as clodronate is, but they still actually stopped the cells from growing. They still had a toxic effect. So that told us that they must work in a different way. So trying to figure out how amino bisphosphonates work was a bit like a jigsaw puzzle, really. And one piece of that puzzle was actually a discovery from a group at Bristol Myers Squibb in the early 1990s. And they found that these amino bisphosphonates could block an enzyme in a really important metabolic pathway in cells called the mevalonate pathway. It's the pathway that produces cholesterol in cells, but the pathway is really important for all sorts of other aspects of cell function. Another part of the jigsaw was a finding we made in the 1990s that actually blocking that cholesterol pathway is toxic to cells. It causes a type of cell suicide called apoptosis. And anything that blocks that pathway, any kind of drug, including statins, which also block that pathway, could cause the cells to die and could stop osteoclasts from resorbing bone. So then the picture started to come together, the sort of jigsaw, parts of the jigsaw puzzle, because it became clear that by blocking that cholesterol synthesis pathway, these amino bisphosphonates could actually have an effect on osteoclasts that altered their ability to resorb bone. It changed their shape, their ability to stick to bone, and produce the acid and enzymes that the cells need to resorb. And then a few years later, a few groups showed that there is one particular enzyme in that pathway which the bisphosphonates inhibit, an enzyme called FPP synthase, farnesyl diphosphate synthase. And actually, the bisphosphonates are really potent inhibitors of that enzyme, and differences in their clinical potency are probably related to their differences in ability to block the activity of that enzyme.
Thank you, Mike. So your biochemistry degree really kicked back in. That's fantastic. Now, so basically, we've got bisphosphonates, but as you mentioned, they fall into two groups, and one with the ATP analogs, one with the mevalonate pathway, FPP synthase. Does that matter clinically or to patients? I'm just wondering if there are any clinical implications.
Yeah, I think it does, because you know, one of the most common side effects with the amino bisphosphonates is this flu-like reaction that some people have, particularly after the first round of treatment. And that probably, again, is related to the way that these drugs work and block that mevalonate or cholesterol synthesis pathway. So what we think causes that flu-like reaction is that the bisphosphonates probably get into other types of cells other than the osteoclasts. And we think probably macrophages, a type of immune cell. And what happens in those cells when the bisphosphonate gets into them is that they produce a molecule, a small type of lipid, which activates other immune cells, gamma delta T cells. And it's those gamma delta T cells that then produce lots of inflammatory mediators like TNF, and that is probably what triggers the acute phase reaction.
Okay, thank you. And yeah, I mean, that's something as a clinician that we're familiar with. And I always tell patients, I used to tell them, don't worry, it's not the flu. Now I tell them, don't worry, it's not COVID-19. Anyway, we move on. So there have been huge advances, as you've outlined, into what we know about these drugs. Are there any other surprises around the corner, either with mechanism of action, or perhaps you alluded to the fact that maybe other pathways or other cells are affected? Your thoughts, Mike?
Yeah, I think there are still surprises in store. You know, for a long time, we thought that bisphosphonates really only worked in the skeleton and acted very specifically on osteoclasts, which they do. But I think there's more and more evidence that these drugs have other beneficial effects. So in particular, there's more and more evidence that they might reduce mortality and have a survival advantage in women with early stage breast cancer, for example, in the osteoporosis setting, and also even in patients in intensive care setting as well. So we've been trying to understand how bisphosphonates have those effects and whether it's through mechanisms that are independent of their effect on bone. So we've got some really interesting data that watch this space. Will be coming soon. We think that these drugs probably do have effects outside bone, probably on macrophages, and that may well explain some of their beneficial effects.
Thank you, Mike. Well, Mike, thanks. It's been absolutely fascinating. Also interesting to hear that there may be more yet to come. I really appreciate your time today. I'm sure that the people that are looking at this interview and the whole series of interviews will find it informative and exciting. So thanks once again, Mike. Thank you.
Always a pleasure. Thanks, Stuart.
Bye.